Hi, my name is Daryl Barnes and I'm with BarnesBasics, and we're going to continue in our Kinematics series, and the videos that are associated with this problem 4A, 4B, 4C, and 4D are found at Hymenopterous Wars 2015. This is an actual thing that happened to me this fall, and so as we work through these problems, you're going to kind of hear my story just a little bit. This is problem 4A. He realized the hymenopterans were getting stirred up and began moving south at the initial velocity of 1.0 meters per second. Keep in mind that I had already been stung multiple times. And so it's true that I started from an actual speed and not from zero at this moment. After 1 second, he was stung, at which time he accelerated in the same direction at 0.45 meters per second squared for 4 seconds. We're going to assume that we have constant acceleration in this problem. It says, how far in meters did he travel as he was vacating the area? What was his displacement? Remember that distance is how far a person travels, and displacement is how far from the beginning point is the person in the end. There are a couple of equations that I want to feature. I want to feature velocity, or average velocity is equal to distance divided by time. And then I want to feature this displacement equation. Displacement is equal to initial velocity multiplied by time plus 1/2 of the uniform acceleration multiplied by the time. So one thing that might be important for us is to write down some of our data. The initial velocity is equal to 1.0 meters per second in a direction of south. And the time right at first is 1.0 seconds. And then it kind of like shifts into a different type of a problem. I got stung and then I began accelerating. And while I was accelerating, I already had a constant velocity. So that's where this equation right here comes in. So at the time I got stung, my initial velocity was 1.0 meters per second in a direction of south. I accelerated at 0.45 meters per second squared. And I did that for 4.0 seconds. 4.0 seconds, that is equal to my time. So I have initial velocity, acceleration, and time. We're going to be using the TI-84 Plus and the TI-Nspire cast to solve these problems. And so remember that if you have not already taken time to configure your TI-84, click on for your calculator, clear, and then if you hit the mode key, then you can use your nav pad to make sure that you have normal, fixed 6, decimal, real, degree, and math print listed, and then hit second and quit to get out of that screen. This, by the way, is described in detail in the very first video of this series called BarnesBasics Kinematics. When we look at the TI-Nspire CAS, if we hit the on button and we're home, then if we use our navigation pad and go to settings and then go to document settings, then we could also use our navigation pad to go through and make sure that we have float, 6, degree, normal, and approximate in the list here, and then go all the way down to the bottom and use your nav pad and then go to OK, and that will apply this to the document that we're using. I'm going to hit escape because I've already done that, and in the TI-Nspire CAS I'm going to go ahead and nav pad over to the bottom left to the multiply, divide, minus, plus. That will open a math document, not a scratch pad document. So we'll come back to that in just a minute. When we look at the question, it says, what is his displacement? So there was a brief amount of time that he was not accelerating, or actually it was me. I thought I was going to be able to get out of here without getting hurt. And so what happened is I want to know how far did I travel in this initial period. And so I'm going to solve for d. So I'm going to say velocity is equal to distance, displacement divided by time. I'm going to multiply both sides by t. And I'm going to have the equation. I'm going to use the equation d is equal to v multiplied by t. And you might even ask, well, why didn't I use the average velocity? Because there was not an average velocity. I was like a bullet out of a barrel. I had an initial velocity, and so we're going to just use this equation for the first second. So my initial velocity was 1.0 meters per second, and the time that I spent doing this was about 1 second, 1.0 seconds. So I'm going to cancel seconds, and I'm not going to even use a calculator on this. I'm going to say 1 times 1 is 1.0 meters, and that's going to be in a direction of south. Now it says, which is true, I was moving south away from this side of attack, and I just picked up the pace rather rapidly. And so we're going to plug into this next equation next and see what we can get for a total displacement. So I was moving at 1 meter per second in the direction of south. And now though, we're blending in the acceleration into this. And so this equation is going to deal with that 4 seconds that I was accelerating. What is the acceleration, or the distance when I was accelerating, but I had an initial velocity. So the time here that we're going to put is 4.0 seconds. 4.0 seconds. And then we're going to add this to 1/2 of the acceleration, which is 0.45 meters per second, and the time squared, which is 4.0 seconds squared. I probably shouldn't have broken this apart because I'm going to get second squared here, and I've got second squared here. Those are going to cancel. I've got seconds over seconds. I'm going to get meters added to meters in this equation. So we know that 1 multiplied by 4 is 4. So let's go ahead and just not worry about trying to put this in the calculator. Let's just say that this simplifies down to 4.0 meters. And let's just kind of worry about what's happening over here. Now, what I have found with my students over the years, it's a little bit counterintuitive. But instead of trying to put all of this straight in, I kind of go backwards. In this equation, I'm going to put 4 squared and then multiply it by 0.45 and then divide by 2. That's how I'm going to get this expression. We could put it in like this, and it's very possible. And in some of the later equations, I'm going to probably use some of the neat tricks that we can see in the TI technology, but I think I'm going to keep it pretty simple in this one. So to solve this little expression right here with the TI-84 Plus, I'm going to hit on, I'm going to hit clear, I'm going to hit 4.0, and there is an x squared key along the left side, the left middle. Hit squared, and then I want you to go ahead and hit enter. Multiplied by 0.45, enter, I got 7.2, divided by 2, and hit enter. And so I got 3.60000. 3.6, and I've got float 6, so I've got 5 zeros behind here. No surprise, and that's meters. Okay, so let's think about this because we're actually almost finished with this problem. I have 1.0 meters per second. That has 2 sig figs. The 1 is significant because it's a whole number, and the 0 is significant because it is to the right of a whole number, to the right of a decimal. Same thing, 2 sig figs. We have 2 whole numbers, 2 sig figs, and the same rules apply here. We have 2 sig figs. So we're wanting 2 significant figures in our answer. So we can We can eyeball this, I think. 4 plus 3.6 is 7.6, and we want 2 sig figs. So let's go with 7.6 meters, and that is 2 significant figures. That is to the south. It does say how far in meters did he travel as he was vacating the area. It doesn't necessarily say what was my distance when I was accelerating the whole time. So we need to add this number, 1.0 meters and 7.6 meters, and we need to get our final answer. And I'm kind of running out of room, and so why don't we just say this? Why don't we say 1.0 meters to the south added to 7.6 meters to the south makes 8.6 meters to the south, and I'm going to say that that is my displacement. It actually is my distance as well, because it's in a straight line. I didn't zig and zag, or I didn't go out and then come back. So good job, everybody. Nice job. Kind of seems complicated, but I think we did a decent job here. So when we add both of these two values up, when we add them, we go 1.0 meters added to 7.6 meters. We get 8.6 meters south. That is the displacement D. I like that a little bit better because it kind of goes from left to right. I don't really like what I did over here. So make sure you think about that when you try to make your teacher happy. Make it easy for them to see what you did.